Good morning, physics folks. This is Dr. Brown. This is our basic concepts video for the study of two-dimensional collisions. This is our introduction to the classic physics problems categorized as glancing collisions. There's a very high probability that you'll see at least one of this type problem on your upcoming mechanics test. The general concept and the use of this can be demonstrated using a pool table. If this is our cue ball and that's our 8 ball, we'll have the cue ball strike the 8 ball and the 8 ball travel and go in the side pocket. So that's the kind of physics application we're looking for. And again, this is glancing collisions. So we have two masses, our cue ball of mass 1 and our 8 ball of mass 2. And we have the cue ball, the M1, colliding with mass 2. A typical type problem would be something as shown here. Two pool balls, the white cue ball and the black 8 ball, both of mass 145 grams, are involved in a glancing collision. Initially, the cue ball is traveling at 15 meters per second to the right, and initially the 8 ball is stationary. After colliding, the 8 ball travels at an angle of alpha, 25 degrees up, and the cue ball travels at an angle beta, 45 degrees down. What is the final velocity of the 8 ball after the collision? What is the final velocity of the cue ball after the collision? Okay, so we've got two masses and we have two questions we've got to solve for. In a situation like this, energy is always conserved and momentum is always conserved. Kinetic energy is conserved if this is a perfectly elastic glancing collision, and we're not told that this is a perfectly elastic glancing collision, so we cannot use 1/2 mass times velocity squared, conservation of kinetic energy, because some of the kinetic energy is converted to sound energy and heat energy. So we have to pursue this as a conservation of momentum problem. So back to our problem here. So we've got cue ball banging into the 8 ball, cue ball going at this angle. This is alpha and that's beta. And we're given these two angles, and we're given the speed of the cue ball, the initial speed of the cue ball, the initial speed of the 8 ball, which is velocity of 0 meters per second. And we're asked to find the final velocity of the 8 ball, final velocity of the cue ball. So we have a before and an after situation. Before and after. Okay, before and after. So applying our conservation of momentum strategy, momentum is designated as P. Momentum is mass times velocity, and these are vector quantities. So we have momentum equals mass times velocity. What we have to realize is that there is conservation, and since these are vector quantities, there are two sets of equations. There's a conservation of momentum concerning the x component. We've got to decompose this vector of the 8 ball and the vector of the cue ball into its two components. There is conservation around the x direction and conservation around the y direction. So the initial momentum equals the final momentum. And when that's decomposed in its two parts, the initial x component of the momentum equals the final x component of the final velocity for the x and the y components both. So when we expand this equation, we will have this, and the momentum in the y direction will have this equation shown here. So again, the before in the x part equals the after in the x part, as the before in the y component of the velocity vector equals the y component after the event. So this is before the event and after the event. And the event is when the cue ball strikes the 8 ball. Okay, so we're going to start populating these variables and solve two simultaneous equations. We've got two unknowns, and therefore we must have two equations. this is the way the problem is set up. It simplifies very rapidly. We should recognize three very important things. The mass 1 equals mass 2, so we can factor all the masses out. Some problems have this, some do not. I've made this a fairly simple problem. The second thing we should recognize is the velocity, the V2, which is the velocity, the initial velocity of the 8 ball is 0. So all of those parts are going to drop out. The third thing to recognize is that the velocity V1 has no Y component. Well, as we stated, the cue ball is traveling to the right. It is traveling only along the x-axis, so it has no y component of the velocity vector. So with these three things, the masses being equal, we can factor out all the masses. There is no V2, or actually V2 is 0, so those parts drop out, and there's no y component to the velocity of the cue ball initially. So these equations simplify quite a bit. This first set of equations simplifies to the initial velocity along the x-axis equals the final velocity along the x-axis. That's the x part of V4. So we're looking at, this is V4, this is the velocity of the cue ball. I'm looking at the x part. So this velocity, again, is, if we decompose it, it is recomposed or composed of two parts, an x part and a y part. So we can do vector addition and add this to this and get the resultant vector. So I have velocity initial on the x equals velocity of the cue ball along the x plus the velocity of the 8 ball along the x. And I can do the same thing on the other side. And so these simplify. So these are our two equations we've got to populate and solve. Okay. If I remember my trig functions, that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, I can see, that, and I'm given these angles, I can solve for these different components. And when I populate the cells using the actual data given, I'm given the initial velocity and the angle of the 8 ball and the angle of the cue ball, and start populating those. Again, the initial velocity of the cue ball is 15 meters per second. The 8 ball, at the final direction of the 8 ball is 25 degrees above the horizon. The final direction of the cue ball is 45 degrees below the horizon. When I start populating these, I will get the velocity, the velocity of the cue ball equals, that's this velocity is going to equal the x part of this and the x part of that. When I start populating these cells, and again, we're decomposing this to the x part of this V1. That's going to be the cosine of 0, which is 1 times V1. The x part of V4, this is V4, I'm looking for the x part here, so that's going to be V4 times cosine of 45 plus the x part of V3, and that's this along the x-axis component of that velocity. Since it's a vector, it has we can decompose it into two parts. So I've got V3 times cosine of 25. When I punch in my calculator, cosine of 45 is 0.707, cosine of 25 is 0.906. I simplify these. This equation becomes V3 equals 16.6 minus 0.780 V4. So that is a simplified first equation that I have. So I have that equation, and I start on the second equation. One thing to realize is that if we establish y up being positive, then that makes y going down negative. So I've stuck a negative sign here. That negative sign is because this V4 is going down, as shown in the drawing. So if we simplify this equation, we will end up with V4, I'm sorry, V3 times 0.423 minus V4 times 0.707, and I used my first equation when I figured out what V3 was in terms of V4 and substituted in here. And again, that's substituting this in here and simplify that equation. I come up with my V4 equals 6.77 meters per second. I then used that number and substitute it back into my equation to solve for V3. V3 is 11.3 meters per second. So that is a very abbreviated way to calculate the velocity after an event occurs for two masses that have suffered a glancing collision. So initially the cue ball had a velocity of 15 meters per second, and initially the 8 ball had a velocity of 0 meters per second. After they collided, and we were given that the 8 ball traveled up at an angle of 25 degrees and the cue ball traveled down at an angle of 45 degrees, the 8 ball will be traveling at 11.3 meters per second, and the cue ball will be traveling at 6.77 meters per second. And again, you should probably expect a problem like this on your upcoming mechanics test. Please let me know if you have questions. Thank you.